Group 14 elements, sometimes called the carbon family, are carbon, silicon, germanium, tin, and lead. In the Earth's crust, carbon is the 17th most abundant element. Silicon, the second most abundant element in the Earth's crust, contributes 27.7% of the crust's mass. It is easy to argue that carbon is the most versatile of all the elements. It is found in nature, both in its elemental state as well as in compounds. It is an essential component of all living things. Organic chemistry is the study of the compounds that contain carbon. The work of many talented chemists is devoted to this very important element. The element is found in several different forms in nature: coal, diamond, and graphite. It is found in a range of compounds in nature, including carbonates, hydrocarbons, and carbon dioxide. Since carbon can combine with sulfur, hydrogen, and chlorine, it forms a wide range of compounds that are used for everything, from medicines to plastics. Carbon is essential for a number of biologically important substances as well. Two stable isotopes exist for naturally occurring carbon: carbon-12 and carbon-13. Almost 98.9% of naturally occurring carbon atoms are found as carbon-12, with 6 protons and 6 neutrons in the nucleus. The remaining 1.1% of carbon atoms are carbon-13, with 7 neutrons in the nucleus. A third isotope of carbon is the unstable carbon-14. This radioactive isotope of carbon contains 6 protons and 8 neutrons in its nucleus. With a half-life of 5,750 years, it is used in radiocarbon dating. In nature, silicon is found in silica and silicate compounds. Silicon is a very important constituent of ceramics, glass, and cement. Germanium is found only in trace amounts in the Earth's crust. Germanium was one of the unknown elements whose existence had been predicted by Mendeleev based on the gaps in his periodic table. Tin is a silvery white metal, as shown in the photograph on the left, with several allotropes. When a bar of tin is bent, it makes a characteristic sound called the cry of tin. Tin is mostly found as the ore cassiterite, shown in the photograph on the right. Cassiterite has the chemical formula SnO2. Lead is a very soft, greyish metal that is shiny when first cut. Lead has been used since ancient times. But lead poisoning can cause many serious health problems, especially in children. Lead occurs in nature mostly as galena, which has the chemical formula PbS. Both germanium and silicon are important semiconductor materials. Ultra-pure samples are used to manufacture transistors and semiconductors. All the group 14 elements have 4 valence electrons. The electron configurations of all of them end as ns2, np2. However, despite the similar valence configurations, their inner cores do vary down the column as the D and F sublevels become available. In general, atomic radii increase down a column, and this pattern is observed for the group 14 elements too. The increase is substantial from carbon to silicon, but it is less pronounced from silicon down to lead. The slower increase from silicon to lead is a result of the completely filled D and F sublevels in the heavier family members. In general, ionization energy increases from left to right. The group 14 elements have higher ionization energies than the elements of group 13, as shown in the illustration. In general, ionization energy decreases down a column. Generally, this is true for the group 14 elements. But notice the small increase from tin to lead. This is due to the poor shielding provided by the D and F electrons, along with the increasing atomic radius. In general, electronegativity increases from left to right across a period. Notice that the group 14 elements are slightly more electronegative than the group 13 elements in the same period. In general, electronegativity decreases down a column. However, silicon, germanium, tin, and lead all have very similar electronegativities. In terms of their physical properties, all the group 14 elements are found as solids. Their metallic character increases down the column. Carbon and silicon are both non-metals, whereas germanium is a metalloid. Tin and lead are both soft metals with low melting points. The melting points and boiling points of the group 14 elements are much higher than the corresponding group 13 elements. For example, silicon has a melting point of 1693 Kelvin. But the melting point of aluminium in the same period is 933 Kelvin. With their 4 valence electrons, the group 14 elements typically achieve either a +4 or a +2 oxidation state. Compounds with a +4 oxidation state are generally covalent in nature. Because of the high sum of the first 4 ionization energies for the group 14 elements. Carbon and silicon are more likely to be found in a +4 oxidation state. It should be noted that sometimes carbon is found with negative oxidation numbers. Try to answer these independently before checking the answers. What is the oxidation number of carbon in each of the following? Methane, CH4. Carbon dioxide, CO2. Ethine or acetylene, C2H2. Assigning oxidation numbers is an important skill. In methane, the carbon is -4. Remember that in compounds, hydrogen often has an oxidation number of +1, and the sum of the oxidation numbers must be 0 for a neutral compound. In carbon dioxide, the carbon is +4. Each oxygen has an oxidation number of -2 here. In ethane, the carbon is in a -1 oxidation state. Again, each hydrogen is +1. So the carbons must be -1 for the sum of the oxidation numbers to be 0. The heavier members of the family are more likely to show +2 oxidation states than the lighter members. This is because the outermost s electrons, which are paired, don't participate in bonding. Thus, it is observed that germanium most commonly exhibits a +4 oxidation state in compounds, and only rarely a +2 oxidation state. Tin is found in both +2 and +4 oxidation states in compounds. For example, the tin 2 chloride and tin 4 chloride forms. Tin in a +2 state is a reducing agent. That is, tin 2 tends to lose 2 electrons or oxidize to achieve a +4 oxidation state. Remember that a reducing agent is the species that oxidizes itself. Lead forms stable compounds with a +2 oxidation number. Compounds with lead in a +4 oxidation state are strong oxidizing agents. This means that lead-4 can gain 2 electrons, forming the lead-2 ion. Remember, the substance that undergoes reduction can be called the oxidizing agent. Tetravalent compounds, such as carbon tetrachloride, have 8 electrons around the central atom. Carbon always obeys the octet rule. Such electron-precise molecules would not be expected to act as electron donors or electron acceptors. Carbon cannot achieve an expanded octet. However, the other members of group 14 can form species with expanded octets due to the presence of unoccupied d orbitals. For example, silicon, germanium, and tin all form complex ions with sp3d2 hybridization around the central atom, as shown here. All the group 14 elements form oxides when heated in oxygen. For example, if wood charcoal is strongly heated and placed in a glass jar containing oxygen, carbon dioxide will form. There are 2 main types of oxides: monoxides and dioxides. It should be noted that silicon monoxide is found only at high temperatures. In general, the higher the oxidation number of a group 14 element, the more acidic the resulting oxide will be. Thus, we observe that carbon dioxide, silicon dioxide, and germanium dioxide are all acidic oxides. The dioxides of tin and lead are amphoteric. For the monoxides, carbon monoxide is neutral, while germanium monoxide is acidic. Like the dioxides, the monoxides of tin and lead are amphoteric in nature. Try to answer this question on your own before checking the answer. Which group 14 element forms the most acidic dioxide? Answer: carbon dioxide is the most acidic dioxide in group 14. In water, carbon dioxide reacts to form carbonic acid, H2CO3, a weak acid. Carbon, silicon, and germanium do not react with water. Tin will react with steam in a single replacement reaction, as given here. Lead does not react with water, most likely due to the protective oxide film that forms on the surface of the metal. The group 14 elements react with halogens of group 17 to form halides. With the exception of carbon, they can react directly. For example, the reaction of silicon with chlorine produces silicon tetrachloride. Germanium, tin, and lead are able to form halides with the general formula MX2. The stability of these halides increases down the column. Most of the halides with the general formula MX4 are essentially covalent in character. The exceptions are the tetrafluorides of tin and lead, which are ionic. In the MX4 halides, the central atom exhibits sp3 hybridization with a tetrahedral geometry. The tetrachlorides of the group 14 elements, with the exception of carbon tetrachloride, are easily hydrolyzed by water by involving unoccupied d orbitals. For example, consider the hydrolysis of silicon tetrachloride. The silicon atom in SiCl4 accepts a lone pair of electrons from a water molecule, forming SiCl3OH and HCl. This process then continues 3 more times, eventually forming SiOH4. As the smallest member of the group, carbon exhibits some anomalous behavior as compared to the rest of the family. This is due to its higher electronegativity and ionization energy, as well as the lack of vacant d orbitals. Carbon has only s and p orbitals available for bonding, and therefore can only accommodate 4 pairs of electrons. Unlike the other group 14 elements, carbon cannot achieve an expanded octet. One unique property of carbon is its ability to form multiple bonds. Carbon can form double and triple bonds with itself and with other small atoms such as oxygen, sulfur, and nitrogen. These multiple bonds are pi bonds caused by the sideways overlapping of the p orbitals. Because of their larger orbitals, the heavier atoms in group 14 do not overlap effectively, and so do not exhibit this type of pi bonding. Another notable property of carbon is its tendency to covalently link with other carbon atoms to form chains and rings. This is called catenation. The carbon-carbon bonds are very strong. As a result, elemental carbon exists in several allotropes, and organic compounds have a wide variety of possible structures. The tendency to show catenation decreases down the group. Silicon shows a less ability for catenation than carbon, followed by germanium and tin. Lead does not exhibit any catenation.